Okay, there it goes.
Okay, so the reason why I made linear algebra the first chapter of the book is that linear algebra is used a great deal in quantum mechanics. And there are all sorts of theorems in linear algebra results that are important in quantum mechanics, and that somebody teaching quantum mechanics doesn't have the time to tell you about or to explain. And so, so that's why I think it's important to go over linear algebra as the first thing. Some of you may be taking quantum mechanics right now, or you, if not, you'll be taking it next semester or next year. The second reason is that linear algebra is a field now in which you can basically do everything in a few seconds with modern computers, including even just ordinary laptops. There are there's all sorts of software available that can basically solve any linear problem in microseconds, and so it's really useful to know about linear algebra. So let me, by the way, remember, you ask a question, you get candy. There's a website. The website for the class is quantum.phys.unm.edu/466-19. And, and I put the first two homework assignments there. Homework is important because if you work out problems, you understand the subject better than if you just read and understand the proofs of the theorems. And the proofs are really very short in this book. I've made them as short as I could. So it's important to do the homework. What do you do with the homework? Well, if you produce the homework as a PDF file, then you should email it to the grader, and the grader's email address is on the website. If you print it out or you do it in longhand, then just put it in his box. And I would say by 3 o'clock on the due date. The due dates are Fridays now. And the first due date is not this Friday, it's next Friday. If you want to get in touch with me, my email address is on the website. If you want to phone me, the problem is that I block calls that aren't contacts, aren't my contacts. And so I don't know how to distinguish a phone call from one of you from just a robocall. I'm in my office typically every afternoon. On the other hand, I tend to get there late. You can be pretty sure that I'll be there by 4, but I may not be there by 9 in the morning or 11 or even 1 in the afternoon. Okay. All right, so let me just remind you, I'm sure you know this, a complex number. Yeah.
Office hours, so does the grader have, and I don't want one,
Right.
I appreciate your thought, but does the grader have office hours, and would you be considering having office hours?
Well, why don't we just say whenever you want to come, I'm there, as long as it's after 4, you know, Monday through Friday, and I'm even on the weekends I'm there. So just come by. In fact, the best thing is to send me an email.
Okay, and the grader, is he?
I don't know what the grader's policy is. Oh, I should mention parenthetically that there's a problems course that goes with this. It's called 468, and it would be useful for you to take the problems course as well as the regular course, the one you're in. And the problems course meets in a room that is usually empty on the weekends, of course. And the grader often is in that room on the weekend. So if you want to see that, but you can send the grader email and ask him. If you guys really want to get to me by phone, here's my iPhone. You can make yourself a contact, become a contact, and put in your phone number, and then you can get through. So here, why don't you just pass it around. If you don't intend to call me, then don't bother to make yourself a contact.
Is there some, I'm not sure I understand.
It's, all right, here. There you go. That's my wife and kids on the cover there. Okay, so this is a complex number. The complex conjugate is x minus iy. It's sometimes written this way. So one uses a star or a bar to indicate complex conjugation. I assume you know a lot about complex numbers, and the inverse of a complex number is the complex conjugate divided by the number times the complex conjugate. This is then a real number, and you've got a complex number in the numerator there. And so that's one way of thinking of them. Arrays. Well, arrays are ordered sets of numbers, and the numbers can be real or imaginary. A one-dimensional array is a multiple, is an entiple, and we sometimes write it like this. It's a column vector, or it could be a row vector like that. And of course, you can add arrays if they have the same dimensions. So, for example, a two-dimensional array, the element of the ith row in the jth column would be aij, and you could add aij plus bij, and that gives you the ij element of the sum of the two arrays. In this case, they're two-dimensional, so you can think that they're called matrices. On the other hand, one can also add arrays that are of higher dimension, like that. It's the same principle. If they have the same structure, then you can just add them like that. There are a couple of ways of multiplying them. One way is, suppose we have two intervals, A and B, then we could say that ABIK is AIBK. This is called an outer product. And of course, it's a very simple idea, an outer product. And it's actually used a lot in quantum mechanics. And but in quantum mechanics, until Dirac introduced his notation, it was awkward to manipulate outer products. This outer product, then, we can think of it as a vector A and another vector here, B. And we can write that in Dirac notation this way. There's more about Dirac notation that we'll do on Thursday, but I'll just mention it briefly like that. On the other hand, if we have two arrays, AI and BK, one can of course make the other BI AK, and so this would look like that. And I guess that's sort of the same outer product, but if one instead does the inner product, then this would be the sum of AI with BI over all of the elements of the two intervals. So those are inner products, and in Dirac notation they look like this. If the arrays are complex, then this one means that we've complex conjugated the array, the interval B, and the same thing here. But as I said, that's got to do with more details about Dirac notation than I'll do on Thursday. These things are called inner products, and of course they're very useful in quantum mechanics, as you no doubt know. Matrices are two-dimensional arrays. The trace of a matrix A, which is sometimes written as trace A like that. This is the sum of the diagonal elements of a matrix. That's the trace. And this, you might think that that's H bar, and in fact it's TR. I was once in a class where I missed one lecture, and when I came in and I saw TR all over the place, I thought it was H bar. I was under that misapprehension for quite a while until I finally realized what he was talking about. It turns out that traces are independent of the order. So this is a sum of AB II over I. So this is a sum of I, but this is AIK BKI summed also over K. And if we rewrite it as the sum over I and K, BKI AIK, we see this is the trace of BA. So traces are, the order of the trace of two matrices doesn't matter, and what one says is the traces are cyclic. So the trace of ABC is, we can imagine, think of AB as one matrix, and this is the trace of CAB. And so you can take the last one and pull it around. And so similarly, trace of ABCD, Z is trace of ZABC down to Y, say. So, those are some properties of traces. Another thing that one can do with a matrix is take the transpose of the matrix. So A transpose IJ is AJI. Mathematicians call this A prime IJ. But in physics departments, we use primes usually to mean something else, a different matrix rather than the transpose of the same matrix. So I use this clumsy symbol, I think. I think we'd actually be better off following the mathematicians. But, this is what I did. Now, what you can show is that AB transpose is actually B transpose A transpose. And if a matrix is equal to its transpose, then A is symmetric. So that's an important property of matrices, and when a matrix is symmetric, it's special in that way. Although, in fact, one can take any matrix and write it as a symmetric matrix plus an anti-symmetric matrix. For example, you just write Aij as Aij plus Aj over 2 plus Aij minus Aj over 2. This piece is anti-symmetric. And a matrix is anti-symmetric if A transpose is minus A. I guess I should have mentioned that, so let me just do that. One important matrix is the Kronecker delta, or one important symbol is the Kronecker delta. Kronecker is the name of a mathematician, early 20th century, mid 20th century. Anyway, this is 1 if I equals k, 0 if I is not equal to k. And the identity matrix I is the matrix delta. That is to say, IIK is delta IK. So, any questions? The inverse of a matrix, I suppose you know this also, the inverse of a matrix is such that one can write, if you form the matrix products A inverse A or AA inverse, you get the identity matrix. And a matrix U whose adjoint, so let's see, did I define adjoint yet? Hold on. Yeah, I forgot to tell you what an adjoint is. So let's skip that. A adjoint Ij is a Ji complex conjugate. So you take the transpose and the complex conjugate. So another way of saying it is, it's A transpose complex conjugate.
Is that a T? Is it, sorry, the symbol above the first A, is that a T?
That's a dagger.
Okay.
It's probably a stupid notation. It's the one that was in use when I was a student. I don't know. I wouldn't be shocked if mathematicians had a better symbol. So it's the transpose complex conjugate, and this is called the adjoint, or it's often called the Hermitian adjoint after a mathematician named Hermite, who was a French mathematician, 19th century or maybe early 20th. Yeah, there it is, late 19th century. French. So, if you have a matrix such that its adjoint is its inverse, that is to say, U adjoint U is the identity, U adjoint is the identity, then it's said to be unitary. And of course, in quantum mechanics, there's a lot of talk about unitary matrices. And basically, if you change from one basis to describe states in quantum mechanics to another basis, you do so with a unitary transformation, a unitary matrix. A matrix O is orthogonal, or a real unitary matrix is orthogonal. So O is such that O transpose O and O transpose are the identity, and O star is O. So an orthogonal matrix is a matrix such that its transpose is its inverse. Orthogonal unitary unitary matrices are all square matrices. And I guess symmetric and anti-symmetric matrices are also. Well, maybe they don't need, I guess they have to be square. 1, 2 is 2, 1. Yeah. Okay. A matrix A is non-negative if all, here I'm using Dirac notation, and I'll say what this is. This would be a sum of VI complex conjugate AIJ, VJ. This is greater than or equal to 0 for all complex vectors. And so this means that the matrix A is non-negative.
And the complex conjugate has a star, right? Not the dagger, the star, right?
That's a star.
Okay.
And so that's a matrix that's non-negative if this is always strictly greater than 0, then we say the matrix is positive or positive definite. I'm skipping the examples in the problem session tomorrow at 5 in room 1131. I think that's the number. It's around the corner there. I'll do several of the examples, and you people, I guess, will also do examples on the board simultaneously. It's not as though I have one of you stand up and do an example and the others watch. Instead, everybody would be doing examples at the same time.
So is that for...
Actually, now that I think about it, I don't know how we're going to do that in 1131 because the blackboards are terrible in there. What did you say?
Are you saying tomorrow for the examples? Is that...
The problem sessions are Wednesdays at 5 o'clock. Right, and you're welcome to come to the problem session whether or not you register for that course.
Okay, so room 10...
I think it's room 1131, but you know, I'm going to talk with the people who schedule classes and point out that that's a terrible room for a problem session. You want a problem session, you want a room ideally like this with lots of good blackboards. That's a room with one or two bad blackboards.
Okay, so Wednesday's 5 o'clock.
Tomorrow, 5 o'clock, 5 to 6, or 5 to 5:50.
The problem session is not necessary for credit for this class, though.
It's what?
Is the problem course necessary for credit for this class?
You can take the problems course for credit. You don't have to. It's independent of this course, and I think it's credit, no credit. It's not a graded course, and it's only 1 credit. You're welcome to just come to the problem session, whether or not you register for it. The department would be better off if you actually did register for it, because I think the university gives departments credit according to how many students take courses. And so if you're in a situation where you don't have to pay for courses, then it would be good if you registered for it. And as I said, it's just credit. Now let's see, various people asked a question but didn't get candy because I forgot. You were one, right? Anybody else? You asked one just now. Anybody else? Well, actually, yeah, you're the camera person, so yeah.
Wait, can I get the organic ones?
What?
Oh, no, you don't have them anymore.
Yeah, they discontinued
Those
these.
were my favorite ones.
Huh?
Those were my favorite.
I know, I really tried to get them, I complained. Anybody else? All right, well, just ask your question real quick. Okay, vectors are things that you can multiply by numbers and add together. Of course, we normally think of them as one-dimensional arrays of real or complex numbers. But the concept is more general. Now, a basis for a vector space, well, let's say, first of all, as I said, you can take vectors and multiply them by numbers. So x, v plus y, u. Let's suppose v and u are vectors, x and y are real or complex numbers. Then this is again a vector, and you could add z, w, and so forth. If you consider the set of all such combinations for all the vectors in a given set, then that's the vector space generated by that set. And when one normally thinks about the vector space is one imagines that one has a basis, which is to say a set of vectors, basis vectors, and let us say n of them, k going from 1 to n, so b1, bn, and then you can multiply u1, b1 plus u2, b2 plus ... plus un, bn, and if you let the u's run over all real numbers, you get one vector space. You get, I guess, the real vector space generated by the vectors, basis vectors b. Or if you let the u's run over all complex numbers, you get the complex vector space generated by the basis b. Normally, of course, if we think of the vectors in the basis as intervals of real or complex numbers, and so if the basis vectors are real, then we multiply them by real numbers. If the basis vectors are complex, we normally multiply them by complex numbers. So that generates the whole vector space. Vectors are, these vectors might be a norm, might be orthogonal, and if bi dot bj is 0, then the two vectors are orthogonal. This, if the vectors, this is if they're real, and if instead they're complex, then one would take the complex conjugate of the ith one and the jth one, and then one would sum over k, say, and this sum, this would be the inner product of bi in direct notation. It would look like this, and if that's 0, then the two basis vectors are orthogonal. If they're real, then it's just the ordinary. In fact, in physics, we're familiar with dot products, and that's why I wrote a dot there. So if they're real, it's just a dot product. Here, if they're complex, then it's you take the complex conjugate of one and dot it into the other. And if that's 0, then they're orthogonal.
So real is dot product.
Excuse me?
Real is dot product, and then complex is this last line.
Let's see, I don't quite understand.
So
What
real,
you-
you take the dot product.
Excuse me?
Real, you take the dot product of the numbers are.
Well, in both cases, yeah, normally if they're real, all you do is take the dot product. If they're complex, you take the complex conjugate of one and then dot it into the other. So there are various examples there, and I'll talk about some of them in the problem session tomorrow. Linear operators. So a linear operator, let us say A, it maps vectors V in its domain. So that's the key word here, domain. The key words here are linear operator and domain, into vectors which I would just write as AV in its range. So what you have is typically the vectors are vectors in some vector space, and A maps the vectors in the vector space into, well, their image, which is the linear operator times the vector. And the fact that it's linear means that let's see, what notation did I use? A on BD plus CW is BAV plus CAW. And this is true whether B and C are real or complex. So this is what we mean by linear. So the operator is linear if it does this. And it's a simple idea, but it's an important idea. And it's a very general concept. Now, in most cases, the domain and the range are the same vector space. And in this case, A will map a particular vector VI into a sum AKI BK, where these are the basis vectors of the vector space. So suppose these are, let's see, I haven't explained what a basis is yet. A basis for a vector space, maybe I hope I did explain it somewhere. Anyway. Oh, okay, good. Thank you. So a basis for a vector space is a set of vectors so that you can write any vector at all as a linear combination of the basis vectors multiplied by real or complex numbers. This is a linear operator, and this is how it acts on a particular basis. And this matrix here represents the linear operator A in the B basis. Now, if we change the basis to some other basis, then the matrix that represents the same linear operator, but in a different basis, will be a different matrix. And let me go through this let me say it this way. So let's see, A on V is A on a sum ui bi, so V is a particular vector that's a linear combination of the basis vectors, and we can write this as the sum ui A bi, and we can, in as much as we have A bi is this, we can say that this is a sum on I and k of ui aki bk, and we can also rewrite this in a trivial way as aki ui bk. So the effect of the linear operator A on a vector V that's represented this way in this basis is the matrix A summed over I and k with the coefficients of the vector and then multiplied by the basis vectors. So if we think of V prime as A V, and we write this as a sum UK prime, sorry, that's a B, BK, then what we would have here is that UK prime would be a sum AKI UI. So let's see. So what happens, in other words, is that if you have a vector that's represented this way in terms of the basis vectors, and you have a linear operator that's represented this way in terms of represented by that matrix, then the image of the vector V under the linear operator A is the vector V prime that is represented in the basis B by the product of, that is to say, U prime AU. In other words, it's the matrix A that represents the linear operator times the vector that represents the vector in this case V. And this is the vector that represents the vector V prime in the B basis. Okay, now, so this is in the notes that you presumably got in front of you. And a somewhat subtle but important point is that each linear operator is unique, but the matrix that we use to represent the linear operator depends upon the basis that we're using. And if we change the basis, then the matrix that represents the linear operator changes to reflect the change in basis. And in particular, if we change the basis this way, we say B prime I is a sum UKI BK. Wow, there's a typo. Let me just signal that. If we change the basis, we go from the B basis to some other basis, and this is a set of vectors that can, this is a set of basis vectors that can represent any vector in the vector space, and so another arbitrary basis is just some linear combination of those basis vectors. So this is some other arbitrary basis for the same vector space. And now, if we go from one basis to another, what we want here is a matrix that's, the coefficients have to be a sensible set of coefficients. In particular, we want the inverse matrix to exist. So that if this doesn't have an inverse, then these vectors defined in this way will not form a suitable basis. Then it turns out, and I'll just, the proof is here, equation 164. You can then write, just as bi prime is that, bi is then the sum u inverse ki b prime k, k equals 1 to n. So, not surprisingly, if you go from the unprimed basis to the primed matrix by multiplying by a matrix U, then you use the inverse matrix to go backwards to the original basis. And then, if you ask, well, what happens to a basis vector b prime I? Well, this turns out to be a sum UKI AJ K U inverse LJ times B prime L. And what that's saying is that the matrix that represents A in the B prime basis is the matrix A prime whose coefficient, whose entries are A prime Li is the sum U inverse Lj AJK UKI. And in matrix notation, what we would say is that the matrix that represents the linear operator A in the prime basis is U inverse AU, where A represents the matrix in the unprimed basis, and U is the matrix that takes us from one basis to the other. U and U inverse takes us back. So that's what happens to these, that's what happens when you change basis. All right, let me now, let's see what the time, oh, we're getting, oh, it's, so I do have some time left. Okay. I've been worried during this lecture that I was going to go too slowly. I think I've gone fast enough. Let me now talk about inner products. And this is something that you might not have had as an undergraduate. So let's first of all look at a positive definite inner product. And again, these are important because they're used all the time in quantum mechanics. So what does it do? It takes any two vectors, f and g, in some vector space, an ordered pair, and associates a number, fg. And in fact, in Dirac notation, we'll write it this way. And these are the rules that it has to be. So in other words, if an inner product takes two vectors and associates them, maps the two vectors into a single number. And the number satisfies these rules. The number fg is the complex conjugate of the number gf. This is an inner product. Well, that's what I'm talking about, of course. Zg plus wh, this is zfg plus wfh. So this is linear. But it's linear on the second element. In quantum mechanics, we'll often deal with complex numbers, and so on the first element, it turns out to be antilinear. By the way, somebody wrote this for another class, so it doesn't apply to this group. Now, as I said, positive definite. The positive definite rule is that this is non-negative and ff equal to 0 implies and is implied by f equals 0. So that's basically the picture, that you can have an inner product of a vector with itself be exactly 0, but then the vector is in fact the 0 vector. So this is a positive definite inner product, and in quantum mechanics, basically the probability that one state would be measured to be, or that a system known to be in one state, say G, is measured to be in another state, F, is the inner product of the vectors that represent those two states, the absolute value of that inner product squared. That's the probability of that measurement. So it's because of its central role in quantum mechanics that I'm emphasizing this. The first rule is that the inner product be Hermitian. The second one is that it's linear in the second element. And the third one is that it's positive definite. It turns out that the first two rules imply that it's antilinear in the second element. In other words, Zg plus Wh comma F is Z complex conjugate Gf plus W complex conjugate HF.
So you said complex conjugate. In this case, are you representing it?
I'm using a bar here, and I use a star in another place. Is
okay. Yeah. So
the bar and star mean the same thing.
Okay.
Sometimes I feel like writing a star. Sometimes I feel like writing a bar. The bar is just one stroke. A star is 2 or 3 strokes. You sure you don't want any candy? You burned several candies.
Oh, I find that
No? Okay. All right, so that's a positive definite inner product. Another inner product is called a Schwartz inner product. And the hardest part about a Schwartz inner product is spelling the name Schwartz, because there are at least 6 different spellings that are in common usage. So a Schwartz inequality, a Schwartz inner product obeys the first 2 rules, but only the first part of the third rule, that is to say, it's positive definite. And then it also obeys the 4th rule, because the 4th one is a consequence of the first 2. So that's the Schwartz inequality. In other words, you have FF is non-negative, But then what you can do is you can show that this implies that GF vanishes for all G in the vector space. So, so the thing is almost positive definite. You can have FF. I'm sorry, this was an equal sign. You can have FF vanish, and that doesn't mean F is 0, but it means that F is orthogonal to every vector in the vector space. So it's almost the same. The inner products of these the inner products of a vector with itself, in the case of a positive definite inner product and a Schwartz inner product, these are non-negative. But in physics we use also indefinite inner products that can be negative, and of course the dot product of two vectors can easily be negative, and we also have four vectors that are used in special relativity, and then those four vectors can of course be negative. For example, P prime can be written as P vector dot P vector prime minus P0, P0, this is the first component, or some equally often or even more often, you put a minus sign here and a plus there. So there are there are four vectors with indefinite inner products that are used in special and general relativity. And in fact, in general relativity, the distance, the squared invariant distance between 2 points is GIK dxi dxk, and this is summed over I and k from 0 to 3 or 1 to 4, depending on how you're counting. And then G, this is the metric of space-time. And the way in which general relativity, the key insight Einstein, one of the key insights Einstein had when he invented general relativity was to say that it should be, that the equation should be the same no matter how you, no matter what coordinate system you pick. So if you change the coordinates, things, the equation should look the same. And in particular, if you have coordinates with these x's, then the squared infinitesimal distance between 2 points is given by this. If you change your coordinates, well, that's fine. This remains the same, you just have to change the metric, and the metric changes a particular way. And the way the metric changes is just the natural way a metric would change. Anyway, this is described in, I don't know, chapter 10 or something of the book. The norm of a vector can be defined in terms of for the case of a positive definite matrix, positive definite inner product or a Schwartz inner product as the square root of the inner product of a vector with itself. And once you have a norm, you can normalize a vector, and we often use hat for a normalized vector. So if we take f and divide it by its norm, then this is a unit vector. That is to say, the inner product of f with f will be 1. We can define two distances. The most commonly used distance between two vectors is just the norm of their difference. But there's another one that is in use especially by people who well, never mind by who, but anyway, let's just call it the Bohr distance, and that's the arc cosine of the absolute value of the inner product of the two vectors. So this is a little bit elaborate there. Okay, there are various other examples that I'm going to skip. All right, now here's a definition. This isn't something that we're going to be using very much, but actually it's a collection of definitions. A vector space that has a positive definite inner metric is called an inner product space. It's also called a metric space, and it's also called a pre-Hilbert space. Hilbert was an early 20th century mathematician. A sequence of vectors, Fn, is a Cauchy sequence if the difference between, so we have two sequences of vectors here. No, I'm sorry, we just have one. So it's a sequence of vectors, Fn, is a Cauchy sequence if the norm of the difference of any two of them is smaller than any epsilon, as long as n and m are greater than some big number associated with epsilon. So in other words, pick any tiny number epsilon, 10 to the minus 6. So we take epsilon equal to 10 to the minus 6, then we can find some big integer, capital N. If n and m are bigger than capital N, then the difference between the two vectors, or the norm of the difference between the two vectors, is less than epsilon. That's called a Cauchy sequence. In other words, you go far enough out in the sequence, then the vectors get very close to each other. A set of vectors converges if the norm, Fn minus f, goes to 0. And an inner product space is set with a norm as I've defined it here, the positive definite inner product. That is complete if every Cauchy sequence converges to a vector in the space. So we say then that the space, the inner product space, is complete if the Cauchy sequences converge to vectors in the space. And a Hilbert space then is a complete inner product space.
So, when you say Fn minus f goes to 0, because in the book it's is that equal to less than epsilon? I mean,
Well, all right. What I mean by this is, given any epsilon, however small, there is an n of epsilon, some huge integer, such that if n is greater than big N of epsilon, then the norm of Fn minus f is less than epsilon. So that's what we mean by a sequence converging to a vector f. So the sequence f of Fn converges to f if, given any epsilon, however small, there's an n depending on that epsilon, such that if little n is bigger than capital N of epsilon, then f sub n minus f has a norm less than epsilon.
And does it matter that the order is different on the board than like Fn at the front minus f?
Oh, well, that doesn't matter, because if you look at the definition of norm, it's independent of the sign.
Okay.
It's the inner product of the vector. In other words, norm, the norm that I'm talking about, okay, so there is this fancy norm I'm mentioning it once, you'll never hear it again probably from me. The norm I think about is the square root of the inner product of the vector with itself. And it's a positive definite inner product, and so this thing is non-negative. And it's 0 only if f is 0. So this is the norm I'm talking about. So this thing here is the square root of the inner product of fn minus f. Okay, well, I hope it's okay. So it turns out that every finite dimensional inner product space is complete and is a Hilbert space. An infinite dimensional complete inner product space is a Hilbert space. And one such space is the space of all square integrable functions. And so that's why in quantum mechanics, when we talk about states, if we get serious, we say that the wave function is square integrable. That's because the space of all square integrable functions forms a Hilbert space being a complete inner product space. Okay, so let's see. Cauchy-Schwartz inequalities. Let's see if I can put some of this in there. If you have any two vectors, f and g, the Schwartz inequality is the inner product of f with f times the inner product of g with g is always greater than or equal to the absolute value squared of the inner product of f with g, which of course is the product of f with g times the inner product of g with f, because this is the complex conjugate of that. In other words, gf So this is the Schwartz inequality. And how does one prove it? Well, what one does is one uses the positivity of inner products. So one considers the inner product of f minus lambda g with itself. And this, you can see if you just use the axioms, this is minus lambda bar gf minus lambda fg plus lambda squared gg. And this has to be greater than or equal to 0. So it's getting a bit late, so let me just say that what you then do is you then choose, you can first of all exclude the possibility that g with itself vanishes, because then if g is 0, then both sides of the Schwartz inequality turn out to be 0, and consequently it's automatically true. So you consider the case where g with itself is has an inner product that's non-zero, and then you make a choice for g. I'm sorry, choice for lambda, and you set lambda equal to gf divided by gg. And if you do that, substitute that in there, what pops out is, after a couple of cancellations, what pops out is the Schwartz inequality. The Schwartz inequality is very important. And you can see that it's so very, very general. You take any two vectors in any positive definite inner product space, and you have that ff times gg is greater than or equal to the absolute value squared of the inner product of f with g. And so that's a pretty important thing. All right, there's maybe one or two more concepts, and one of them is that of linear independence and linear dependence. And this is a remarkably simple but very important concept. And so what is it? It's basically that if you have some vectors, C1, V1 plus C2, V2 plus, what did I say, Cn, Vn, and this is equal to 0, the vectors are linearly independent if the only way this, I'm sorry, let me say linearly dependent. They're linearly dependent if there are coefficients C1 through Cn such that this is true and not all the C's are 0. So the V's are linearly dependent if there are C's not all 0 such that the sum of the C's times the sum of the vectors is 0. So if you can find a linear combination of the vectors with coefficients, some of which are non-zero, they're linearly dependent. If you can't, they're linearly independent. And of course, when I say you can't, I mean you using a computer and the right program and so forth. So that's the idea of linear independence. And a set of linearly independent vectors in a vector space is maximal if there's no other vector that you can add to the set that keeps the set, the enlarged set, linearly independent. So that's the idea of a maximal set. And it turns out that if you have then a maximal set of linearly independent vectors in a vector space, that forms a basis for the vector space. And you can write any vector in the vector space as a linear combination of these linearly independent vectors. They form a maximal set. All right, I think we're basically out of time. There's the issue of exams. As I said, I think what we should have is grading based on homework plus, I guess we'll have a final exam, and why don't send me email if you want a midterm. Some people like midterms. Some people don't like midterms. We don't have to have a midterm. In fact, I'd be happy to get rid of grades altogether, but the department insists on grades. All right, are there any questions? Any more questions? Does, did anybody not get a candy who asked a question? Does the videographer want a second candy?
Yeah, she would like one.
Okay, so might as well turn the thing off now. Just press that button there.